Just to explain some details. Okay.
We are live.
Ok, bom dia a todos, sejam bem-vindos ao segundo dia do segundo workshop do Cloud-HPC. Hoje a gente vai começar com a palestra do professor Gabriele e mais tarde a gente vai ter a sessão de trabalhos de alunos de iniciação científica e pós-graduação às 2 horas no link que foi já enviado por e-mail. Tá bom? Essa palestra ela vai ser em inglês, então eu vou apresentar o nosso convidado, tá bom? I'm going to now to switch to English to introduce our guest. Okay, Gabriele. First, I would like to thank you, Gabriele, for accepting this invitation to be present here in our workshop. Gabriele Mencagli is an associate professor in the computer science department at the University of Pisa in Italy. He has co-authored about 60 peer-reviewed papers appeared in international conference, workshops, journals, and in one book. His research interests are in the area of parallel and distributed system and data stream processing. He's a member of the editorial board of Future Generation Computer System and Springer Cluster Computing. And today he's going to talk about towards next generation stream processing system. Gabriele, it's up to you. You can share your screen for us.
Okay, thank you. Can you hear me?
Yeah, we
yeah,
can hear
thank you. Yeah, I will share the screen. Let me know if the sharing is working. Okay, do you see the screen?
Yes, perfectly.
Yeah, we can see, but it's not your slide. Yeah, we can see.
Now, okay. If there are any problem of networks or you cannot see the screen or something like that, let me know, because I'm not looking at the chat. So please stop me if there are any problem of network or something like that. So I'm assuming that you see the slides so I can start, okay?
Okay, we are seeing your slides.
Can you hear me?
Yes, Gabriele, we can hear you. You can start.
Thank you so much for this invitation to do the invited talk to your workshop, Leandro. Yeah, okay. So thank you for the invitation for giving this invited talk and the activities that I'm doing at the University of Pisa, Department of Computer Science. And it is about data stream processing systems. Okay, so first of all, I would like to, hello?
We hear you, Gabriele, with some delay and not hearing anymore.
Is not working.
Yeah, we can hear you, Gabriele.
Hello, can you hear me?
Yes, we can.
Gabriele, maybe if you turn off your camera here. Caiu, né? Pessoal, vamos guardar um pouquinho. Probleminha normal de transmissão, né, Leandro?
Sim, é verdade. Vamos esperar ver se ele consegue reconectar.
Ela também está com um pequeno delay entre o teu áudio e a tua imagem, mas é normal, não prejudica.
Sim.
Can you hear me? Leandro, can you hear me?
Yeah, we can
Yeah, now I
hear
changed
Gabriele.
I changed the network.
Okay.
So I hope that this network now is much better.
Yeah.
Give me one second that I move. Sooner or later I will connect.
Yeah, we are seeing your screen.
Yeah, 1 second, because I'm downloading otherwise I have to switch to the other computer. I don't know what happened, but give me 1 second, please. I'm sure that with this network, everything should work. Unfortunately, today here in my home with the network provider that I have, we are experiencing many issues, and I don't know why. And I didn't have the possibility.
It's okay, Gabriele. Don't worry.
Okay, sorry.
It's okay, don't worry, Gabriele.
Is giving me just but I hope that after this. Okay, can you see the slide?
Yeah, we can see, Gabriele. You can go
Okay,
ahead.
thank you. So now I will start, okay?
Yes.
Okay, thank you so much. Sorry for the problem. As usual, there are many technical issues. Okay, so today I have the pleasure to start this seminar about stream processing and next generation stream processing systems. So I would like to talk about the research that we are doing at the University of Pisa in my research group. First of all, I would like to spend 1 minute to describe my university, but just 1 minute, because I think it's nice to show the city and the university in which I'm working. I am an associate professor at the University of Pisa, which is one of the oldest universities in Europe, founded in 1343. The university has 20 departments, and also, in particular, the oldest computer science department in Italy, founded in 1969. And this is my research group, Parallel Programming Model Group, working in the field of parallel programming, high-performance computing, data stream processing, and something like that. This is my boss, Professor Danielutto, and this is mine. Okay, so first of all, what is the outline of this talk? The outline will be the following. I will introduce what is data stream processing and the evolution of systems for data stream processing applications. In the first part of the presentation, I will show what are the research directions to configure and to use stream processing systems on scale-up architectures. We will talk about different models for implementing stream processing systems. I will show some research prototypes, and in particular, the research prototype that we are developing in Pisa. In the second part of the talk, I will introduce what are the research directions for pushing data stream processing at the edge. So we talk about how to use coprocessors that are often available in edge computing devices. And I will talk about how to customize the scheduling of stream processing systems. So first of all, there is a huge difference between streaming and non-streaming. Okay, what is batch processing? Batch processing is a set of techniques and systems for processing huge amount of data But differently from stream processing, this huge amount of data is immediately available as a permanent static data set that is available in memory or in a distributed file system, and you can immediately use this data set for your analysis to produce outputs. On the other side, instead, in stream processing, you still have huge amount of data, but you don't have this amount of data immediately available, but you are continuously receiving data one by one from as a stream, as a sequence that is in motion, dynamic, and unbounded in size. So inputs are not immediately available, but you have to process them one by one. Of course, stream processing is extremely critical for what regards performance. Because if you are not able to process this huge amount of data that you are receiving at high speed with sufficient performance, bottlenecks are very common, and the quality of your analysis decreases a lot, or even you can obtain results too late for your analysis. So performance is extremely critical, and there are many relationships with high performance computing. So to do that, there are many stream processing systems that exist in the world. Systems specifically targeting the analysis of streams with high efficiency. And we talk about them in this first part of the presentation. So first of all, in this first part, I would like to introduce what is data stream processing in a more theoretical way. And I would like to introduce what is the evolution of streaming systems. So first of all, what is a data stream? A data stream is a real-time, continuous, ordered sequence of items. You cannot control the order of the items that arrive, and you cannot store all the inputs that you receive in memory, because otherwise you will saturate your memory. So the key characteristics are the unbounded nature, and that all the inputs are not available in advance. In particular, in the early stages of stream processing, one item that you receive from the stream is a tuple of different fields. So it is a structured record of attributes. For instance, in this case, this is a typical situation of a network application in which you have one item from the stream that is a tuple with different fields, a timestamp, source IP, destination IP, and so forth. But as we will see, stream processing applications evolve a lot, and now we can have items that are not records, but something more complex. But what is important to understand is that with stream processing, we needed a paradigm shift. In the old DBMS that still exist and are very important, data are persistent in the sense that you have the data in the database and you don't modify the data so frequently, but in many cases, you have to analyze the data, you have to execute queries that are transient and produce a result. So in the traditional database community, queries are one-shot. Instead, data are persistent. Instead, in the streaming domain, you are in the opposite situation. The queries are permanent. The user decides to run a query that is a long-running application that continuously produces new outputs as soon as new inputs are available from the input stream. So you need a shift. And so the same systems that we use for analyzing databases are no longer sufficient for our analysis. In particular, what is a data stream processing application? A data stream processing application is essentially a directed acyclic graph of operators connected with each one. What are operators? Operators are components, nodes of this graph that perform transformation of data. So you start from data sources that can be file systems, memories, sensor, whatever. you have a stream of data and operators apply intermediate transformation steps until you have the final results that are delivered to the user. And this computation can create new knowledge, discover hidden knowledge in the data, compute aggregates depending on the specific application domains. And what is important is that, of course, there are many progresses in algorithms for processing streams in a quite efficient manner. For instance, avoiding to buffering all the inputs that you receive, but maintaining intermediate results from which you can continuously update the answer of your application, the output of your queries. But this is not only a matter of new efficient algorithms, but it is also a matter of implementing such kind of continuous queries in a quite efficient way on the available hardware that you have. There are many parallelism dimensions that exist. Operators in the query can run in parallel on different inputs. They can be replicated to increase the bandwidth of the computation. So there is an inherent parallelism inside the queries. But let's talk a bit about streaming operators. What are the boxes that you have inside a streaming application? Operators can be of different kinds, and this poses a serious problem in the parallelization of the whole application. We can recognize operators that are completely stateless. For instance, operators in which, like a filtering, imagine what we have here in this part of the picture. This is a selection operator that is a filter that receives a stream of inputs, and suppose that this operator drops all the inputs that are not equal to A. So, for instance, in this case, B is dropped. This is a stateless operator because the decision of dropping or not a specific input depends only on the values of that input. So you can easily parallelize such kind of computation, but you have also more complex operators that are stateful because they need to keep a history of what they have received so far. For instance, imagine what you have in this second part of this picture. This is a join operator on stream. And this is very similar to what we have on databases, but with the difference that now streams are unbounded. So every time you receive a new input from the first stream, you have to compare this input with all the inputs that you have received so far from the other stream in order to detect when the join predicate is satisfied and to emit results. So theoretically, you have to buffer all the inputs that you received. In other cases, not only operators are stateful, but they are also blocking. Imagine to have a sorting. It's very easy to sort a finite data set because you have all the inputs. But if you have to sort a stream, this means that you have to see all the inputs of the stream before completing the sorting and produce results, because otherwise, without any other information, you don't know if you can keep the right ordering, if you don't know what you will receive in the future. So in many cases, streaming operators need additional primitives for changing their semantics with respect to traditional databases. In particular, for instance, one important paradigm that is very popular in stream processing is the use of sliding windows. What is the idea of having a sliding windows? Is that not all the inputs have the same value for you, but what you have received recently is much more important to what you have received in the past. So you are giving much more value to the recent inputs that you have. And this is something that is available with different paradigms, with different APIs in all the stream processing systems that exist in the world, in which you have the possibility to change the semantics of these sliding windows by changing when inputs are expired from the windows, and when new inputs instead trigger the execution of a window that is considered complete. Just to give you the idea of this, you can have windows that are count-based, in which you have a fixed size of the window and slide every fixed number of inputs. In this case, the slide is 2. Every time you have 2 new inputs, you delete the oldest 2 inputs, you add the new ones, and you can restart the computation over all the inputs of the window that you have. But you have also time windows, in which you have, in this case, imagine a window of 8 seconds. So you are buffering all the inputs that you receive in the last 8 seconds, and then after every 2 seconds, you update the windows that you have. So you delete the oldest inputs, you add the new ones, and you repeat the processing, with the difference that now each window may contain a different number of inputs. So in all the modern stream processing system, you have the possibility to detect to choose this kind of window semantics. But I would like to go on, because the evolution of stream processing system was very, very fast. We started in 1992, more or less, with the first kind of stream processing systems that were extension of database management system. Indeed, the name was very, very similar. Not database management system, but data stream management systems. In many cases developed by American universities, but not only. But more or less, starting 15 years ago, many distributed data flow systems have been developed. And in many cases, they belong to the Apache umbrella. Many popular systems like Apache Flink, Apache Storm have been developed, open source products that can be used for streaming. So one example of a system of this kind that is very, very popular is Storm. Storm is an open source stream processing system that can be used for running streaming applications, both streaming applications like database queries, but also streaming application working on images, text, or something like that. Starting from a high-level API, the user can build a data flow graph of operators and run those operators on a distributed architecture that can be a cloud of virtual machines, a cluster of nodes, and something like that. The API is mainly in Java, and such kind of system has also important fault tolerance support. For instance, they support one-at-a-time processing, so the user has the guarantee that each input is processed at least one time in case of failures. Another system of this kind is Flink. Flink is another popular Apache system for data stream processing with an API that is fully declarative, in which the user focus not in the interconnection between operators, but in how data are transformed. And the data flow graph is obtained by the system by starting with this declarative API. In this system, Flink, we have exactly one semantic. So we have the guarantee that in a distributed execution, even in case of failures, each input will be processed exactly one time. This is more or less two examples of stream processing systems that are extremely popular. But now I would like to tell you why these kind of systems are not enough. In particular, they are not enough for scale-up systems. What is the idea? What is a scale-up architecture? If we consider scale-out, we have many, many machines interconnected together. So such kind of system for stream processing like Storm, Flink, Samza, Spark Streaming, and many others that I'm not mentioning, they are designed to scale on many, many machines. You can add more machines to your environment. You can distribute your application in more machines, and you increase performance. To do that, these systems have a complex runtime system for distributing part of the computation, for serializing and deserializing data, for taking advantage from a distributed system. But this situation is not equal to a situation, a scenario that we call scale up, in which we have one single machine with a lot of processors, a lot of memories. And in many cases, such kind of big machines are possible. Nowadays, it's very easy to have machines with terabytes of memory, with several tens of cores. And in many cases, such machines are enough for running our stream processing application. And in theory, we don't need to distribute our application on more machines. But unfortunately, the traditional system that exists, that are designed for scale-out architecture, do not provide good performance on single machines, still powerful. For instance, this is a picture taken from a very popular paper published in VLDB 2019, in which the authors compared the performance of stream processing system on a single machine against the theoretical bandwidth of the memory, that give you the idea of what is the highest speed for processing inputs that you have in a scale-up environment. And as you can see, these three bars here are Flink, Spark, and Storm, three popular stream processing systems for scale-out. And as you can see, the bandwidth is very far from the theoretical one. Why? Because there are many overheads in targeting scale-out architecture that when you have the execution on a single machine, you pay this overhead, and this prevents you to achieve satisfactory performance on a single environment. So this is why we need to, let's say, overcome such limitations. And in my research group, we are studying different models for developing and designing streaming runtimes of the future. The problem is the common starting point is to have a single data flow graph of operators. But how are streaming graphs executed on top of a multi-core architecture? We can identify at least three different models of execution. And I don't know what is the winner, depending on the situation. And of course, this is a research direction. On the left, you have the first model adopted by most of the stream processing system nowadays. You start from a graph of the application. Each operator is a thread visible to the operating system, and the operating system is in charge of running the threads according to the scheduler of the operating system. This is thread-based parallelism. The other possibility is operators are not threads. Operators are logical entities that we can say they are actors, like in actor-based parallel programming. So logical entities that the user, according to some user-level policies, decide when they are executed on a pool of threads visible to the operating system. So now you have much more operators than threads. This is actor-based parallelism. But the final idea is also to have tasks that are a little bit different. You start from a data flow graph. Each node of the graph is a logical entity that can be materialized in multiple instances depending on the concurrency limits that we have for each node. For instance, in this case, operator 1 can be materialized in three different occurrences. So every time you have a new input, you compute the new input and the function of the first operator, and this is one task that is available for be executed on a machine. If you have another task, this input with the same function is another task, and so forth. So you have much more parallelism, but you have to schedule this huge amount of tasks on the underlying set of threads that you have visible to the operating system. We call this task-based parallelism. So To study what is the direction that is better, depending on the specific machine, we need to rise a little bit the abstraction level in developing our runtime system. So our idea in Pisa is to build an intermediate layer between the data flow streaming graph and the runtime system. In this way, the runtime system can switch from using tasks, actors, or even threads, but you have an intermediate layer between the data flow graph visible to the user and what is under the hood. The idea is to introduce a set of building blocks. Building blocks that can be parallel or sequential. What are the building blocks that we have in mind? Are building blocks like Lego bricks? If you remember in your childhood, maybe you use Lego to build complex systems. So this is the same idea. We have sequential building blocks. For instance, in this case, this is a sequential building block that corresponds to one node of the graph that processes input sequentially by applying a function f on each input. You have a combiner block that performs the composition of function on the input. So every time you have a new input x, you apply the first function, and then on the output that you obtain, you apply the second function to produce the final result of this block. You can have other sequential building blocks, but even also parallel building blocks, expressing, for instance, temporal parallelism, in which you apply different functions, F1, F2, F3, on different inputs. You have an all-to-all building block that allow you to create complex data flow graph in which each node on the left communicate with all the possible nodes on the right. And you have also modifiers of those building blocks that allow you to create cycles in your graph that can be useful for performing optimization, as I will mention in a while. So the idea is to have data stream processing application modeled as graph, having a runtime system that is based on this composition of building blocks that can be nested together to build a complex graph. And each building block may have different implementations based on different parallelism model, like thread-based parallelism, actor-based parallelism, task-based parallelism, and something like that. This is the idea that we have in our department, in my group. And to implement this idea, we develop a library for stream processing for Scaleup Architecture that is aimed to be a competitor of existing stream processing systems that in many cases are optimized for scale-out environment only. WinFlow is the name of our library. It is a C++ library for stream processing application on single machines. What is nice of this library is that its runtime system is completely based on composition of building blocks, as I will explain in a while. Give me 1 second, please. I will drink a bit of water. Okay, so we can start. What is nice from WinFlow is that we define a stream processing application using a high-level C++ API. So WinFlow is a C++ 17 library. C++ 17 is one of the last standard of C++. What is nice is that you can create operators of your application by using a fluent interface in which you configure the features of the operator, like the parallelism, like the functional logic of the operator by using lambdas or functor objects and something like that. And then you connect operators one by one to create data flow graph of operators. So, for instance, consider what happened to build the application that you have on the left that is composed of a source, an operator that we call the map, an operator that is a filtering, and finally a sink absorbing the outputs. What is nice is that we create a source with parallelism 2, And to create a source, we create an all-to-all building block by having pipelines on the left. In each pipeline on the left, we put the source, that in this case, there are two parallelisms, so two different nodes implementing the source. And then we have on the right side a placeholder. Then when you add the map to the graph, in this case, the runtime system inspects the properties of the source and the property of the map. In this case, the parallelism is the same, and the map is completely stateless. So depending on this property, the compositional rule is to append the map to the pipelines on the left of the all-to-all. Instead, suppose that now we add the filter. The filter here is still with parallelism 2, but now we are using a k-by property for creating this filter. Means that each instance of the filter must receive inputs according to a k-by distribution. What is the idea? That all the inputs of the same type must be delivered to the same replica of the filter operator. This can happen in many cases when you have stateful operators that must process all the inputs of the same kind sequentially. Imagine that you have a network analysis operator that need to process packets of the same connection one by one. So all the packets belonging to the same connection must be delivered to the same replica of the operator. So in this case, the compositional pattern is different, but we can model this. We can add a new all-to-all inside the right-hand side of the outermost all-to-all. So we are nesting the all-to-all in this way. And we have a compositional rule here in which you have a combiner block that combine the map with this emitter functionality that is in charge of distributing data to the filtering in the right way. In this way, all the inputs that are cross are delivered there, for instance, and all the inputs that are circles are delivered there. We can model complex things by using nesting of our building blocks. At the end, for instance, here we have the sync operator that is fully stateless. So the final structure of the application is this one. This is the idea. Of course, we can make this idea more complex. Okay, we can have more complex graph of streaming operators according with our analysis. For instance, suppose that you have, starting from our high-level C++17 API, you start with a source operator followed by a map operator. So you have something like that. Here you have k-by, so you have this complex pattern. But now suppose that the output from the map must be delivered to different operators depending on their properties. So you have to apply different operators depending on the specific kind of outputs that the map is delivering. So in this case, you have to do something like that. You can have a complex graph in which each input produced by the map replicas can be delivered to this part of the system or to this part of the system. So you are using there a more complex building block that is a building block in which each output produced by the map can be delivered to this emitter functionality if the destination is this final operator that is a filter. Otherwise, each output from the map is delivered to this second emitter and will reach this second part of the system applying another map. So we can compose the things and we can use a high-level API for expressing such kind of graphs. So, of course, we can do, using our compositional approach, we can model very complex things in a quite easy way. For instance, in many cases in streaming applications, there are cases in which you can process inputs as soon as they arrive, but there are applications that are more complex in which you assume that each input has a timestamp and you have to process inputs in increasing order of timestamps. So if you have such kind of policies in your application in which you have to process inputs based on their timestamps, this compositional approach helps you. For instance, we can use a special collector node, which assumes to receive inputs in different input streams, in this case, 3 input streams, and we assume that on each input stream, we are receiving inputs ordered by timestamp. So for this collector, it's quite easy to buffer inputs and to emit them in order. So to do that, our compositional approach can add special collectors before the operators in order to guarantee that such ordering is maintained. So if the sources will generate data in order of timestamps, the application will, the runtime system will guarantee that all the operators of the application will process inputs in order of timestamps. And the user is absolutely not involved in this process, but this is just a matter of declaring the application and creating the application using our library in the right way. Okay? 1 second, I will clear, okay? But we can do something else. When you create the operators, you can also express if you want to produce output one by one, or if you want to produce outputs in batches. You know that sometimes producing output in batches can be useful even in a single memory, in a single machine, in order to optimize performance by amortizing the runtime system overhead. And you can do this in a very, very accurate way. For instance, you can decide, depending on the structure of your application, if between, for instance, the source and the map here, inputs must be delivered by one, and instead between map and the filter there and the map there, you must deliver using batches of a proper size. Of course, at the moment, it's the user that is involved in choosing when to use batching or not and of which size. But of course, we are working, because this is possible, to find heuristics for choosing the batch size dynamically. So everything that I'm describing now is based on a specific implementation of the building blocks that we have in a system that we are developing in Pisa that is called fast flow. In other words, we have wind flow, and after wind flow, under the hood, we have the implementation of building block of fast flow. But theoretically, you can replace the implementation of the building blocks in fast flow with other implementation with the same API of the building blocks, and wind flow can continue working. So in fast flow, what is essential to understand is that communication in a single machine is implemented by using efficient lock-free queues. You know that lock-free data structures are data structures for shared memory systems in which you don't have to use locks to guarantee the correctness of using the data structure, because they are based on atomic instructions that are much more efficient in many cases than using locks in an arbitrary way. Fast flow and all the building blocks that we are using are based on these kinds of data structure, in which between the nodes, a node on the left, the producer, and the node on the right, the consumer, we have a lock-free queue in which elements of the queue are not complete messages, but they are pointers to shared data structure that you have in memory. So the idea is that the producer passes to the consumer pointers to access data that have been written and they are ready to be used by the consumer. This paradigm has been proven to be very efficient on shared memory system, and the implementation can be made very efficient. On commodity architecture, passing a pointer on such kind of data structure requires few hundreds of nanoseconds. That is a very small communication overhead. And we can build our building blocks using the abstraction of fast flow. This is the code for creating an all-to-all blocks in fast flow. This code is a little bit complex, but if you are a user of WinFlow, you never have to use this fast flow abstraction, because WinFlow provides to you an API that I shown in the previous slides that is very, very efficient, very, very simple to use, in which building blocks are composed automatically from a high-level description of the data flow graph of operators that you want to develop. So now, what is the comparison with existing stream processing system? If we have WinFlow and we want to compare the performance of WinFlow against, let's say, Storm and Flink, they are for distributed systems. But what happens if we execute Storm and Flink on a single machine? And what can happen if we run using WinFlow? We did some experiments on a high-end server machine with 48 AMD cores and a NUMA organization. In this application, we are not using batching because batching is not available in Flink and Storm. You have to implement it by hand. And so to have a fair performance, we are studying what happened to the performance if we process input one by one without batching. So we use many streaming applications that are available in the literature, applications that belong to different application domains. Fraud detection is an application for detecting frauds of credit card transactions. Spike detection is another application of financial analysis. Linear road is an application for processing in the, let's say, in smart cities applications. The Yahoo streaming benchmark is another popular application. So we have several applications of streaming. Someone is a very small graph of operators, other are much more complex. Let's say this is a big application for the analysis of telemarketing, and it is composed of many operators connected together. The summary of results is a plot that you see in the slide, in which we are using the logarithm scale there to show the throughput that our application are able to achieve. We compare Storm, Flink, and WinFlow. And as you can see, in all the application, using WinFlow against Storm and Flink produces a huge performance improvement of 15 times in some cases to 1 point something in the pessimistic case. Why this? Because our system is more, it is not only a difference between languages, because of course Storm and Flink, since they target the distributed system, they are based on the Java virtual machine for portability, while instead our library is based on C++, that is a compiled language. This is not only a matter of this, it is also a matter of efficiently implementing the runtime system. And this is evident from this other set of experiments that we did about latency. There are many application domains that is not only important how many inputs you are able to compute, but how long you take for computing the output from when the input is available. As you can see here, this is the latency of WinFlow compared with what happened in Flink and Storm. And the difference is huge. In most cases, latency of WinFlow is in the order of microseconds, few microseconds. And if we study what happened to the latency, for instance, here we are comparing what happened in two applications, Linear Road, that is an application for smart cities on the left, and VoIP Stream, this is another application on the right. We compare the time that our latency is spent inside the runtime system code and what is the time that is spent in the operator's code. The time in the operator code, that is the blue part, is of course dependent on the language, because when you translate an application from Java to C++, you are translating the code of your operators. And of course, if you have an advantage on this, means that C++ is faster. But the other part is also the runtime system overhead, that, as you can see, is much, much smaller in our library because we remove a lot of overheads that are present in traditional systems like serialization, deserialization, and many other stuff that are no longer needed when you target a single machine. This is extremely important, and now I will conclude in 15 minutes with the last part. How can we use this knowledge now to target systems that are not scale-up architectures, but they are more resource-constrained devices? Before continuing, can you please give me a feedback that you can hear me and everything is okay with the streaming, just to be sure that everything is working?
Yes, Gabriele, everything is working good. You can go ahead. Okay.
Yeah, thank you so much, because otherwise I cannot see you in my iPad, so it's better to have a feedback. So this is the last part of the talk now. We have a knowledge about how to design runtime system for stream processing in a different way, targeting multi-core architectures. But what happens if you target edge computing, and why it's important to support the stream processing on edge computing devices? Because there are many situations nowadays in the IoT environments in which there are cases in which sensors are close to edge computing devices, and you cannot transfer all the data of the stream to the cloud on analysis, because otherwise the latency for transferring data is too big. So you have to do the analysis closer to where data are produced. In many cases in papers, you see this sentence, no? That you have to move intelligence close to data sources. But using power-constrained devices that are popular in IoT and edge computing is not easy. In many cases, they are more small multi-core architecture like in big servers, but they are different. We use different multi-core architecture, often ARM-based, and in many cases, coprocessors are extremely important in edge computing devices. In edge computing devices, it's reasonable to have coprocessors like integrated GPUs and FPGAs that can be used for accelerating part of your computation, because such kind of coprocessor in many cases consume less power than the traditional multi-core device that you have on such kind of embedded system. But supporting coprocessors is not easy, and no standard tool exists for stream processing. So we are working on two directions, actually. The one that I'm mentioning is the one to develop new stream processing system for edge resources using coprocessors. The other directions is to improve existing stream processing system like Storm and Flink to be more powerful on edge resources. So I would like to spend some minutes talking about the first idea, developing new systems, and then to the second idea, what we can do to improve what exists. So let's start with the idea of having a new stream processing system, not traditional, like WinFlow. In WinFlow, we are using and developing a support for using integrated GPUs. And in particular, we target system-on-chip, small architecture like the Jetson Nano board or Jetson Xavier board by NVIDIA, in which in this small system, you have a small ARM multi-core, typically two, in this case, 4 cores, and you have an integrated GPU that is a very small GPU, in this case, composed of one stream multiprocessor. And what is nice is that these two systems, the CPU and the GPU, are integrated in the same chip, and they share the same memory. So we need also to develop something different rather than using GPUs as we do in traditional server, in which the GPU has its own memory and you have to transfer data from CPU memory to GPU memory by hand or by using some abstractions. So the idea is the following. We have our data flow graph. There are operators that you run on CPU, as usual, there are operators that you decide to run on GPU because they are quite intensive and they want to offload the processing on a device in which you have a lot of cores that you can use with low power. So the idea is that you offload a processing of a batch on the GPU, you compute all the results of the batch in a quite efficient manner, and then you reproduce the stream that is transmitted to another operator of the application. To do that, this situation is quite simple for what regard stateless operators, because if you have a batch, to produce the output batch, all the inputs can be processed in parallel because the computation is stateless, so they are fully independent. So it's quite easy to write a CUDA kernel, if you are using CUDA, in which each input is processed by a separated CUDA thread. But what happens instead if you have a stateful processing, in which not all the inputs of the batch can be processed in parallel, but you have to process sequentially inputs of the same kind, because they belong to the same class of inputs and they access the same state. So in this case, we have developed, but I don't want to enter in the detail because this is not the purpose of this presentation, more complex CUDA kernel to process batches by respecting the k-by properties by running all the inputs of the same k sequentially on a CUDA thread. Of course, if the number of k's inside the batch is quite large, we can use data parallelism and improve performance. For instance, in this picture, all the inputs that are green can be processed in parallel with respect to inputs that are red and with respect to inputs that are yellow. So the other point that is interesting is that in embedded systems with a GPU like this, the CPU and the GPU share the memory. So we need to avoid useless copies, and we need as much as possible to avoid allocating data that can be accessed by the GPU, because every time you create a new buffer that is accessed by the GPU, you have big overhead. So this is why we are using, if you remember, our modifiers of building blocks to introduce cycles that can be used for recycling allocated memory areas in order to reallocate them in the future, but they can be safely overwritten. So every time, for instance, this operator will send a batch to this source, this means that the source can overwrite the content of this buffer without deleting and reallocating the buffer. By using such kind of things, we can greatly improve performance, and we implemented a custom memory allocator from scratch. This is just, I can skip this part, we can create GPU operators in a very simple way. The API is the same of CPU operators, but the only difference is that you provide to the operator functions that are executable by the device. So you don't have to develop explicitly memory transfer, launching of kernels or something like that, because everything is completely hidden to the user and we are exposing a high-level API. So preliminary results with two applications, fraud detection and spike detection on Jetson Nano. We have a big improvement in performance using the GPUs instead of using only the ARM multi-core on the embedded system. We can increase the throughput by more than 3 times with respect to what we achieve using only the multi-core in fraud detection, a little bit less in spike detection because the application is different. And we compare also the performance that we obtain using, for instance, different implementations of the GPU operators that use explicit memory transfer, in which you are duplicating things because you are moving data from CPU to GPU. But we know that on Jetson Nano, actually, we have one memory. So there is the way to share memory between CPU and GPU, and you can avoid copies. And this is what happened with the blue lines that you see, dashed blue lines that provide better performance. So we studied different implementations of these GPU operators, and we are conducting experiments to be sure about the performance, but the results are quite nice. I will skip the part related to FPGA support because I have only one slide. We are working on supporting FPGAs, but this is something that if you are interested, we can talk at the end in the questions. What I would like to tell you now in a few minutes is what we can do in the other direction of the approach. To target edge computing devices for stream processing, we can, of course, using different tools, but we can try to improve the tools that we have. Indeed, if you have an IoT environment composed of several embedded systems like mobile phones and something like that that are interconnected with each other, you can use traditional tools for streaming like Storm and Flink. But in many cases, the performance is not the one that you expect. We can do something better? Yes. And one idea is to work in terms of scheduling. Why? Because the difference between a multi-core machine that is a server machine and an embedded system is that in the server machines, you have many multi-core CPUs and you have tens of cores. If you run an application there, you have several threads, but in many cases, the number of cores that you have available is a quite high number of cores. But if you are running a stream processing application in which you have many threads on a machine with 2 or 4 cores, you are putting a lot of effort to the operating system scheduling that must decide which operator must be put in execution every time. And what I can tell you is that according to our analysis, the operating system scheduler that exists, for instance, in Linux, that is the most popular operating system for such kind of stuff, is a completely fair scheduler that in many cases does not take the right decision, and better decisions can be made if you know something about the applications. For instance, in this data flow graph, for many reasons, I can prefer to give much more priority to the thread running operator B, because in this way, I know that operator B is a bottleneck, has a lot of inputs in the queue. So if you run B much more frequently, you can clear the queue and you can minimize latency. But to do that, you need to change the scheduler. So how to do that? We have 2 possibilities that exist. The one on the left of this picture is the possibility used by many systems in the literature. If you use a Storm or Flink, for instance, in the standard case, each node of the graph is a thread, and each thread is scheduled by the operating system according to the fair scheduler of the operating system. So in many research papers, they change the implementation of Storm and Flink, and now each node of the graph is not a thread, but it is a user-level thread. And there is a user space scheduler that decides which operator must be executed on a smaller number of kernel-level threads that are executed by the operating system. So you are changing a lot the runtime system of Storm and Flink in order to implement a custom scheduling. Of course, you can choose which operator to run on the threads because you have full control, but you have to redevelop from the beginning the implementation of the system. Our idea is instead completely different. In our idea, we have data flow graph of operators. Each one is implemented by a thread visible to the operating system, so we are not touching the standard implementation of system like Storm and Flink, but we have an additional components here that receive the metrics of the application, what is the behavior of the application from the performance viewpoint, and change the implementation or customize the implementation of the Linux scheduler in order to schedule the kernel-level threads in the best way as possible. This system is something that we published in the middleware conference this year. The system is called Lachesis, that is a god in the Greek mythology that was responsible for let's say she measured the thread of life of each person with a rod. Okay, so this is the idea. The idea is we have a system in which you have the stream processing system there that can be Storm or whatever. We have a driver that receive metrics of the running applications, for instance, using system like Grafana, and give these metrics of the running application. So we know every time what is the operator that is slowest, what is the queue size of the slowest operator, something like that. And our system will execute specific scheduling policies that will tune the operating system scheduler. How? For instance, using the nice command. Do you know that in Linux, you can change the priority of the threads using the nice command? Of course, you have some limits, but you can do that. But you can also use real-time threads and other tool provided by the operating system to change the priority of threads. By doing that, without changing the runtime system of Storm and Flink, we can implement custom scheduling. And so I can skip this part. This is one evaluation of our system Lachesis. The experiment were conducted on an Android architecture with 4 ARM processors. We have 2 applications from a benchmark that is available online for IoT applications. We are using Storm, and we are comparing what? Our system that use our optimized, nice-based scheduling policies to help the operating system, that is Lachesis, the orange line. We are comparing with the standard phase scheduler of the operating system, and we respect you another system, the blue line, that is called Edgewise, published in this conference, Usenix ATC in 2019. What is the idea of Edgewise? Edgewise modify completely the runtime system of Storm by replacing the runtime system using user-level threads that are scheduled by the user on top of a fixed number of threads visible to the operating system. So this is the other approach in which you change the operating system. Instead, we are using an approach in which we don't touch the runtime system of the streaming tool, but you are helping the operating system. So as you can see, in terms of throughput, Lachesis is the winner. By increasing the input speed, our system using our custom scheduling on a small machine like the Droid is able to provide much better performance and smaller latency. Consider there that by increasing the input speed, there is, of course, a saturation limit, and then the latency explodes. And this happens in all the system, but with Lachesis, using the same architecture, we are sustaining a higher input pressure by producing lower latency. That means that we are doing a good job. We can do this also on distributed scenarios in which you have a cluster of droids interconnected that mimic an IoT system. And also in this case, the orange line that is Lachesis is compared against the standard operating system, because for the distributed setting here, we don't have experiments on Edgewise. And also in this case, the performance using Lachesis is much better than using the traditional operating system. So in other way, we don't modify Storm, we don't modify Flink, we don't modify the traditional stream processing system, but we have an external tool that monitors the performance of the application and change the priorities at the operating system level of the threads in order to achieve better performance without touching the application, without touching the runtime system of the stream processing tool. So I can conclude, because I'm a little bit late due to the problems that we had at the beginning of the talk. Sorry for this. Today I tried. I know that sometimes I went very fast, but I hope that I gave you at least the idea of what we are doing in Pisa. Creating, developing new methodologies for new tools for stream processing system for big server machines, so scale-up system, and also for edge computing devices in 2 different ways, this latter point, by targeting the coprocessors and in particular integrated GPUs, and we are working on FPGA, and also by improving traditional stream processing systems by using custom scheduling without changing the stream processing system. This is the idea. And I hope that you found this talk interesting. If there are people interested, of course, I'm here for answering questions, but if you have questions in the future, collaboration, something like that, I'm very happy to talk with you.
Thank you, Gabriele, for your presentation. It was very interesting. We are learning too much about data stream systems. We have some questions from the YouTube. Okay. The first question is from Cloud. He has two questions. The first is, with the way you build the workflow of an application, do you care about proof of correctness and debugging issues?
Okay, I'm not sure if I understood the question because there are problems of networks, but you are asking me if we took into consideration problem of correctness of the applications. Yes, of course. Yes, of course. In all the cases that we are developing, in all the applications that we develop, we, of course, take into account the results that we are achieving. We always compare the results according to the baseline in Storm or other systems. So all the experiments that I show you when I compare WinFlow against Flink or Storm, of course, let's say, we are sure about the quality of the results. Okay, so of course the correctness and the semantics of the application sometimes is something that the user knows. For instance, if you remember, I can go back to the slide in which, give me 1 second, 1 second only, I can show you where is there. Okay, if you remember this slide, okay, if you need to process the stream in order, this is a constraints of the semantics of the application. So in many cases, the user has the possibility to decide which kind of configuration of WinFlow is needed to be sure about the quality and the correctness of results. Of course, ordering or not ordering inputs have different implications in performance, but this depends on the application that you have. I don't know if this answers a bit the question.
Yes, thank you, Gabriele. Claude has another question. That is, can you handle multiple flow cases on the same time using a single unified model with the paradigm and tool you have presented for us?
This is a nice research idea. Honestly, at the end, we think that our approach has this capability, but we are working on this, and we did not test the system in such kind of configuration. But we think that from the theoretical viewpoint, yes.
Okay. Another question from Professor Felipe França.
Felipe, nice.
Yeah. He asking about if it has the possibility of adopting some machine learning approach to scheduling or mapping the data flow nodes, especially in IoT edge cloud scenarios.
Yeah, absolutely, yes. We have a student working on this kind of stuff, in which you can configure the scheduling of the operators on the cores of the machine based on a learning of similar applications that have been run in the past, but not only, by also profiling the application during the beginning of the execution and tuning the mapping according to the specific behavior of the application. We are working on this. There are possibilities to use neural networks for such kind of things. There are people working on this. I didn't show you some results, but we have something that we are working on this direction, and of course, nice idea.
Okay. Claude asked about the first question about the proof of correctness in the big issues. They ask if you don't plan to have a proof of correctness by construction, not by comparison of the results.
No, we don't have this. We don't
have this.
But it's a theoretical problem, of course. I think that since the implementation of the system in WinFlow is something that can be done using a formal semantics, because we published in IEEE Transactions on Parallel Distributed System the formal semantics of the composition of building blocks. I think that we can extend such kind of analysis to prove correctness by construction. But because the structure of the building blocks that are recursive may help in doing such kind of formal analysis. So I think that we can do that, but we didn't.
I see. Yes. I have some questions. The WinFlow, they have support to run in the cluster system?
At the moment, we are developing a distributed implementation of the building blocks. We are developing means that the support is not complete. So at the moment, the answer is not. WinFlow is something for a single machine. Of course, you can have several WinFlow processes, but the coordination and the communication can be done using an external tool, like, for instance, let's say Kafka or other message publish subscribe systems. But there is no possibility to write one single WinFlow application and run it in a cluster automatically. You have to split by hand. But we are working on providing a distributed implementation of the building blocks. If we have this runtime, the good point is that since we have a modular implementation, once we have the distributed building blocks, everything should be quite easy to migrate to the distributed system.
Yeah, I see. And they have WinFlow and chassis. They have some. They are storing some public repository.
Yeah, WinFlow is on
using
GitHub.
Collaborate.
Yeah, WinFlow is on GitHub. Yeah, if you Google WinFlow GitHub, you can find the Google page. Yeah, there is also the home page. Of course, the documentation can be improved, because as we know, we are not a company, so it's difficult to find time to write a good documentation, but the code is quite commented. There are many examples. If you download the library is an header-only library, so you don't have to compile the library, you have to include the headers. There are many applications that have been provided with the code as examples, and I think that you can use in a very easy way the library. Otherwise, of course, I'm very happy to talk with people that are interested in using WinFlow for any reason.
Okay. Thank you, Gabriele, again. It was very interesting, your presentation. We don't have more questions.
Thank you so much, and sorry for the problem at the beginning.
No, it was awesome. Your presentation was awesome. Don't worry. Okay? Thank you again. So,
Thank you so
I will
much.
switch to Portuguese just to have some words, ok? Ó, então, pessoal, a gente está finalizando essa sessão aqui com o nosso palestrante convidado, tá? Às 2 horas vai começar a sessão de trabalhos dos alunos de iniciação científica e pós-graduação no link que eu enviei para vocês por e-mail. Eu peço que quem se inscreveu utilize os e-mails que vocês utilizaram no cadastro para logar na sessão, tá bom, pessoal? Então a gente se vê lá na próxima sessão. Até mais.